Today, we'll be covering Section 3.1. Section 3.1 is about basic probability and counting principles. So we'll start with the simple question. What is probability? When we think about probability, sometimes we think about odds, chances, and what it really is it's the likelihood that an event will occur. When we measure probability, we're always measuring it in the same way. We're measuring it in relationship to all possible outcomes. So before we can discuss probability in any great detail, we need a bunch of definitions. So our first definition is the definition of a probability experiment. What a probability experiment is it's any action through which results are obtained. There are a lot of classical examples that we can talk about. Things like flipping a coin, rolling a die, drawing a card, picking a number. But that's not the extent of it. We can discuss probability in so many other different types of probability experiments. Those are just some of the basics. Once we have the concept of a probability experiment in hand, we can next talk about an outcome. What an outcome is it's the result of a single trial in a probability experiment. So this is what actually happens when we perform that probability experiment. When you flip a coin, does it come up heads or tails? That's the outcome. When you roll a die, do you get a 5, a 6, a 2, a 1? That's what actually happens. That's an outcome. After outcomes, we can talk about a sample space. A sample space is the set of all possible outcomes for any probability experiment. So for instance, if you're flipping a coin, there's really only 2 different outcomes, heads or tails. But if you're rolling a 6-sided die, there's 6 different outcomes. 1, 2, 3, 4, 5, or 6. So each different type of probability experiment will have its own set of outcomes, which we call the sample space. Next, we have an event. So what an event is it's some subset of a sample space that has one or more outcomes, so at least one. For instance, if we're rolling a die, an event could be rolling a number that's even, right? So we have the possible outcomes of 1, 2, 3, 4, 5, or 6, but the event rolling an even number would just consist of 2, 4, or 6. So that would be a subset of the entire sample space. That would make it an event. Next, we want to look at an example. You perform this probability experiment. First, you choose a colored marble from a sack with 3 marbles, red, blue, and green. Then you flip a coin. Describe the sample space. So we want to try to determine what that sample space looks like. The way we're going to do this is by first creating something that we call a tree diagram, which is a very visual way to approach this type of problem. So what is a tree diagram? Well, a tree diagram is a visual depiction of a sample space. You take your first action and you write all the different possible outcomes from that first action as branches on a tree. Then, after that's been done, you ask yourself, what's the next action? And each outcome after that has branches representing the next action's possible outcomes. And we keep doing this until we run out of actions. So for example, in this example, we had 2 actions as part of our probability experiment. We were drawing a marble, and then we were flipping a coin. So drawing a marble will have its branches, and then coming off of the end of each one of those branches, we will have branches representing the coin flip. So let's take a look at what that would look like. First, we had 3 choices of marble. So we have 3 branches of our tree: red, blue, or green. Now we don't know which one of these is going to happen. So the second choice, which is flipping the coin, we have to have branches on the end of each one of these initial possibilities. So we put heads or tails after each one of those colored marbles, because the way we figure out our sample space is by starting at the top and then going down all different possible routes. So if we start at the top and we move left, we could go to red for the marble, and if we keep going left, we can get to head for the coin. But we could have gone red and then gone to tails. Or we could have gone blue and then to heads. Or blue and then to tails. Or green and then to heads, green and then to tails. So getting to the end of this diagram gets you all the different possible outcomes. We write that in these curly brackets like so. RH represents red on the marble, heads on the coin. RT, red, then tails. BH, blue, then heads. BT, blue, then tails. GH, green, then heads. GT, green, then tails. So those are the 6 different ways that this probability experiment could result. That's the entire sample space. So how about a practice problem? Describe the sample space for the following probability experiment. First, you flip a coin. Then you choose a colored marble from a sack with 3 marbles, red, blue, and green. Finally, you flip a coin. Use a tree diagram to help. So you'll notice this is similar to the example that we just did, but now there's more actions. Instead of just 2 things to do, there's 3. We flip a coin, then we pull a marble, then we flip a coin. So we're going to have 3 sets of branches in our tree here. So why don't you pause the video, give this a shot, and when you're ready, hit play. Okay, so let's take a look at the solution. Our first action was to flip the coin. So we get 2 branches on our tree. Then we're going to draw a marble, red, blue, or green. So from each of these possible outcomes to the first action, we need to have 3 branches coming off of each one of these. So after heads, we'll put red, blue, green. After tails, we'll put red, blue, green. Then we're going to flip another coin. So the coin will come out heads or tails, but we have to put a heads or tails outcome on each of these 6 colors that we have in the second row. So after red, you'll have 2 prongs. After blue, 2 prongs. Green, 2 prongs, and so on. Then, to figure out your sample space, you're trying to get from the top to the bottom in all different possible ways. So it could be head, then red, then head, head, then red, then tails, head, then blue, then head, head, then blue, then tails, head, then green, then head, head, then green, then tails. And those are all the different ways that the initial coin flip could have come out heads. But what if the initial coin flip was tails? Then it could have been tails, then red, then head, tails, red, tails, tails, blue, head, tails, blue, tail, tails, green, head, tails, green, tails. So that sample space would have 12 outcomes. You can always tell the number of outcomes by counting the number of terminal points at the bottom of your diagram. So if we look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you think of it like a maze, each one of these things at the bottom is an exit to the maze. So there's 12 different outcomes. So we abbreviate those with just letters, H for heads, R for red, and so on. And this is what our sample space looks like. Notice the curly brackets. You always put curly brackets around a sample space. Why is it important to know sample space? Well, sample space is what tells you how to find probability, because we're always measuring probability in relation to the total number of outcomes. So if we don't know how many things are in the sample space, we don't know how to compute the probability. So we've already defined the concept of an event, but now we want to flesh that out a little bit and go one step further and define the concept of a simple event. So a simple event is an event that only has one outcome. Remember, we said outcomes were subsets of sample spaces that had one or more outcomes. Well, a simple event only has one outcome. So example, you roll a pair of 6-sided dice. Determine the sample space. Well, if we make a tree diagram again, we have to think of each die as its own separate number. So if there's 6-sided dice, there's 6 different numbers that could come up. So the first die could be 1, 2, 3, 4, 5, 6. But we don't know which one of those is going to come up on the first die. So the second die has to have branches for all 6 of its outcomes after each one of these. And so that's going to lead us to 36 different possible outcomes in our sample space. And here they are. I've done a little graphic here that actually shows you the die faces. And the reason I've done that is because sometimes people have a hard time understanding that 5 and 1 is different than 1 and 5. But you can see that if you have 5 on the red die and 1 on the blue die, that's really a different outcome than if you have 1 on the red die and 5 on the blue die. So those have to get counted separately. So let's consider this event. Rolling a sum of 2. So we just saw the 36 rolls, and we really have to ask ourselves, how many of those added up to 2? If it's just 1, then it's a simple event. If it's more than 1, then it's not a simple event. Well, the only way you can roll a 2 is by rolling a 1 and a 1. That's it. That's the only way to do it. And so there's only one outcome in this sample space. So that makes this a simple event. What about this one? What about rolling a sum of 6? Is this a simple event? Well, if we think back to those rolls, there were actually several ways to roll a sum of 6. A 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, a 5 and a 1. All those different outcomes would result in a sum of 6. So because it's not just one outcome, but actually 5, this is not a simple event. So, one of the most important concepts in probability is the ability to count, because that's going to allow us to determine the size of our sample space, which is fundamental in computing probability. The first and most important rule for counting is called the fundamental counting principle. The fundamental counting principle says that if event A can be executed in m different ways, and event B can be executed in n different ways, then the number of ways you can execute event A, then event B, is given by m times n. And this can be extended to more than 2 events. So we could do 3 events, 4 events, however many you want. So let's see how this works. Example. At Build-A-Bear Workshop, when you make your new best friend, you have to also choose the clothes for your buddy. There are 22 different shirt styles, 16 types of pants, and 9 different hats. How many different outfits are possible for your bear? So, we're going to use the fundamental counting principle. There are 3 actions that we have to take. We have to choose a different shirt, pants, and hat. So there are 22 different choices for the shirts, 16 different types of pants, and 9 different hats. According to the fundamental counting principle, we multiply these together. And when we multiply 22 times 16 times 9, we get 3,168 outfits. That's how many different outfits we could put together for our new stuffed animal. Let's take a look at another example. The current formula for California automobile license plates is 1 digit, followed by 3 letters, followed by 3 digits. How many different license plates are possible using this structure? So here's a picture of a license plate. You'll see a single digit, then 3 letters, then 3 numbers. So this doesn't talk about vanity plates or, plates where you're writing some name or word or message. This is just the standard automobile license plate. But again, this can be done using the fundamental counting principle. This time we have 7 different slots to fill in. The first one is a number. It's that first digit. Then a letter, a letter, a letter, followed by a number, and a number. So there are 10 digits between 0 and 9, 26 different letters, and for each case 26 letters, because there's no rule that prohibits us from repeating a letter. Then we have 10 choices for the next digit, 10 for the next digit, and 10 for the last digit. The fundamental counting principle says multiply all of these together, and that results in 175,760,000 different license plates. So how about a practice problem? How many 7-digit phone numbers are possible using these rules? So first, the first digit cannot be a 0 or 1. The other digits, though, have no restrictions. So give that a chance, try your best, pause the video, and when you're all ready, hit play. Okay, so this is very much like the license plate problem. We have 7 slots to fill in. This time, they're all digits. In this case, the first digit had a restriction. We said we couldn't allow that first digit to be a 0 or 1, which means instead of 10 possible numbers that we could place in that position, there are only 8. But because the other digits had no restrictions, each one would have 10 possible numbers that we could put in each of those slots. The fundamental counting principle says multiply all these together. And when we do that, we end up with 8 million different phone numbers. Now that would be 8 million phone numbers per area code. But even that is not quite the way that it works. So the way that we set up this problem, this would be the answer. But in the real world, there's actually more restrictions. So, what are those rules? Well, the first digit can't be 0 or 1, so that was part of our problem. But then we can also not start our phone number with 211, 311, 411, 511, 611, 711, 811, or 911. Those are all prohibited. You also can't start your number with 988 or with 555. Those are all off limits. Why? Well, the first digit can't be 0 because if you dial 0 on a phone, it takes you directly to the operator. And so your phone number can't start with that number. Whenever you dial 1 on a phone number, that immediately takes you into the long distance circuit, and the phone system interprets that as you wanting to make a long distance call. So the next 3 digits it assumes is going to be an area code, which wouldn't make sense if you were just dialing a local number. Then what about these 3 number combinations? Well, 211 is for community health services. 311 is for city municipal services, things like garbage collection, sewer line problems, those sorts of things. You could dial 311 for help. 411 is for directory assistance. It's information. So if you dialed 411, they could help you locate telephone numbers, area codes, all kinds of help like that. 511 is for travel and road information. So if you want to know about road closures, if you're planning a trip through the mountains and you want to know about snow or chain requirements, you could dial 511. 611 is for telephone repair service. 711 is for speech and hearing relay service for those people who are speech or hearing impaired. 811 is for before you dig services. So if you plan to be digging on your property, you can dial 811. They'll come out to your home and they'll mark where gas lines and power lines are underground so you don't accidentally dig them up and sever them and cause a disaster. Of course, 911 is for emergency services if you need police, fire, or ambulance. 988 is a relatively new number. It's the suicide crisis hotline. So if you or somebody you know is suffering through a suicidal crisis, let them or you dial 988 for help. And then 555 is a prefix that's reserved for movie industries. So when you're watching TV, you may notice that a lot of the phone numbers in TV shows and movies start with 555. And that's so that people at home don't annoy people by calling that number. So if we tried to incorporate all these rules, what would that counting really look like? Well, if we had no restrictions, that would be 10 possibilities for each digit, which would be 10 million numbers. If we started a phone number with 0, then we would just be choosing the next 6 digits, which would all have 10 possibilities. So there would be 1 million different phone numbers that might have started with 0. And 1 million different phone numbers that might have started with 1. And if we take that 10 million and subtract away the 1 million and the next 1 million, that's really the 8 million that we got as the answer to that practice problem. But let's also incorporate all the other restrictions. If your phone number started with 211, that means you would only be picking the last 4 digits. So they're 10 times 10 times 10 times 10 is 10,000. So there would be 10,000 numbers that would have started with 211. For the same reason, there's 10,000 that would have started with 311. 10,000 that would have started with 411, 10,000 that would have started with 511, 10,000 that would have started with 611, and 711, and 811, and 911. Also, 10,000 would have started with 988 and with 555. So if you count up those 10,000s, there's actually 10 of them. So that's another 100,000 phone numbers that get thrown out. So altogether, there's 2,100,000 phone numbers that are not allowed. So you take the 10 million and subtract away those 2,100,000, and that gives you 7,900,000 allowable phone numbers per area code. So when I mentioned the fact that we want to be able to count, this is the kind of counting that we're talking about. Because you wouldn't want to sit and count each individual possible phone number one by one. We want to be able to use these formulaic methods to help us achieve that goal much more quickly. Now we can talk about types of probability. So there are two main types of probability. First, there's classical probability, which is also called theoretical probability. And in theoretical probability, this is a probability measure where all outcomes are considered to be equally likely. To find the probability of any event E, we take the number of outcomes that are in E, and we divide that by the total number of possible outcomes for that probability experiment. This formula really shows you why it's so important to be able to count, because knowing the number of possible outcomes in a sample space is a fundamental part of the formula to calculate probability. What classical probability is, it's really perfect world probability. It's the probability where all outcomes are equally likely and everything comes up roses. So here's an example. You roll a pair of dice. Find the probability that the sum is 6. So, to solve this, it turns out we've already talked about all the pieces of this problem previously in this section. You may recall we mentioned that there were 36 different rolls for a pair of dice, and that's the size of the sample space here. When we were talking about simple events, we also asked about rolling a sum of 6, and we saw that there were 5 different ways that we could roll a sum of 6. So if we put those pieces together, the probability of rolling a sum of 6 is 5 out of the 36 possible rolls. So there's 36 ways it could turn out, and 5 of those 36 add up to 6. So the probability of rolling a sum of 6 is 5 out of 36. That's how basic probability works. Find out how many ways you can accomplish your goal, divided by the total number of ways that the experiment could come out. So here's a practice problem. You flip a quarter 3 times. What is the probability that the results are all tails? And as a little hint, you might want to make a tree diagram to help you understand what the sample space looks like. So go ahead, pause the video, give this problem a try, and when you're ready, hit play. Okay, so let's take a look at the solution. If we were going to make a tree diagram for 3 different coin flips, the first coin flip could come out heads or tails. The next coin flip could come out heads or tails, but notice we have a branch on each one for heads or tails. Then the third coin gives us the next layer of the tree, also heads or tails, but we put that heads or tails on each one of these branches. So then if we count up the bottom, we can look and see 1, 2, 3, 4, 5, 6, 7, 8. So our sample space has 8 different outcomes. Those outcomes are HHH, so heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So those are your 8 possible outcomes. That tells you the denominator, the bottom of the fraction for your probability. So your probability will be something over 8. The question is, what's that something? Well, we were asked, what's the probability that all of the results are tails? Well, when we look at these different outcomes, there's only one that's all tails. The very last one is tails, tails, tails. So 1 out of these 8 fit that description. So the probability of all tails is 1 out of 8. Then we can talk about the next type of probability, which is empirical probability, also called observational probability. This type of probability is obtained by actual observations or experiments. So it's not theoretical. We're not looking at what should happen. What we're really doing is we're performing an experiment over and over and over again and seeing what actually does happen, right? So how many times did we perform the experiment? That's the total frequency that we see in this formula. And then how many times did it come out fitting the description of the event E? That'll be the numerator, the top of this fraction. So let's look at a practice problem here. You flip a coin 1,000 times. The results are 571 heads and 429 tails. What is the empirical probability that the next flip will be a head? So my little guy here, you'll see him, he says, should I choose heads or would it be better to choose tails? What does the evidence suggest? That's really what we're talking about when we're talking about empirical probability, is what does the evidence lead us to believe? In a perfect world, it's a 50-50 chance whether or not this coin comes up heads or tails. But if we were betting money and we noticed that it seems to be coming up heads more often than tails, then wouldn't we be more likely to bet heads than tails? Doesn't the evidence suggest that heads comes up more often? Maybe this coin is heavier on one side than the other and so tends to land with heads up more frequently. Maybe it's not a perfect coin, right? So we have to take those things into account when we're making some kind of wager or bet, and we really like evidence. That's what empirical probability is. It's about evidence. So hopefully by now you can see what the answer here is. It's not 1 out of 2. It's not 50-50. The probability that the next coin will be a head is going to end up being 571 out of 1,000. Because when we did this experiment 1,000 times, it came out heads 571 times and tails 429 times. So the empirical probability of heads would be 571 out of 1,000. So empirical probabilities don't have to match up with theoretical probabilities. As a matter of fact, they can be wildly different. But if you continue to do these probability experiments over and over and over again and increase the number of trials, then something interesting happens. Something that we call the law of large numbers. And what the law of large numbers says is that if you increase the number of trials of a probability experiment, that causes the empirical probability to approach the value of the theoretical probability. So what does that mean? If we look at that example with flipping the coin, where we flipped it 1,000 times and heads came up 571 times, what would happen if we flipped it 10,000 times? or 100,000 times. And what you would see is it wouldn't necessarily be 1/2 or 50% or 1 out of 2, but it would get closer and closer and closer to that 1 out of 2 number. So the variation would be less and less over time as we get more and more trials. That's what the law of large numbers says. So, if we think about that last example, flipping a coin 1,000 times, let's ask ourselves, what is the minimum number of heads that could have occurred? The fewest number of times that we could have seen heads come up on that coin. Or what's the maximum number of heads that could have occurred? And even though it's hard to imagine, it is possible to get no heads at all, to never ever have that coin come up heads. It's not very likely, but it is possible to flip the coin 1,000 times in a row and get tails 1,000 times in a row. So really, if we were computing empirical probability and we never had heads come up, then the empirical probability of obtaining heads would have been 0 out of 1,000, which turns out to be 0. And on the flip side of that, no pun intended, it's possible that every time we flip the coin, it came out heads. Again, not likely, but there is a possibility for that to happen. So, if we were computing the empirical probability and it always came up heads on the coin, then it would have been 1,000 out of 1,000, and the maximum empirical probability would have been 1. So, when we look at this problem, it actually gives us a range into which all probability values must fall. So, the range of probabilities. For any event E, the probability of E has to fall between 0 and 1. It can be 0 and it can be 1, but it can't be less than 0 and it cannot be more than 1. So to put this in other words, all probabilities have to fall between 0 and 1. Now, these endpoints have special names. If you have an event where the probability is 0, then we call that an impossible event. And if you have an event that has probability of 1, then we say that that is a certain event. So let's take a look at an example. There are 6 colored marbles in a bag: red, blue, green, yellow, purple, and orange. You choose a marble from the bag. What is the probability that it's green? What's the probability that it's not green? So let's put these marbles in a bag and let's think about this, right? The probability that it's green. So if I reached in and I pulled out this green marble, that's just 1 out of the 6 marbles, right? There are 6 different marbles I could have picked. Only 1 of them is green. So the probability of choosing a green marble is 1 out of the 6 marbles. All the other marbles in the bag are not green. That's 5 other marbles. So the probability of not being a green marble would be 5 out of 6. These situations are what we call complementary. These are complements of one another. If one happens, the other doesn't. And their probabilities always add up to 1. Right? Because if we drew a green marble, then we didn't draw a non-green marble. And if we drew a non-green marble, we didn't draw the green marble. Right? If one happens, the other didn't. So we have some rules for complements. So the complement of an event E is the set of all outcomes in a sample space that are not part of E. The complement of E is written as E with an apostrophe, which we say as E prime. So whenever you see E with the apostrophe, we say E prime. And the probability of E is always 1 minus the probability of E prime. And the probability of E plus the probability of E prime always add up to 1. If you think back to that example that we just saw, 1/6 plus 5/6 equals 1, right? Those probabilities added up to 1. And if E happens, then E prime does not. And vice versa. If E prime happens, then E doesn't. We cannot have them both occur simultaneously. So those are the rules for complements. And moving forward, they're going to be very important for us because complements are one of the most powerful tools we have when computing probabilities. So that brings us to an end of section 3.1. Please check on Pearson for your homework and have a great day.